Okay, good morning, ladies and gentlemen. Welcome to chapter 11 from your ukulele textbook. We are going to discuss functional groups today. Um, Before we get into functional groups, I'm just going to ask you a simple question. How would you define organic compounds? You could define it traditionally or give me the modern definition of it. I'd appreciate it if you close your textbooks and to give this answer. Uh, we'll have a think pair share on this. 1 minute to think, 1 minute to pair up, and 1 minute to share your answers. Your time starts now. Thanks. Okay, so the traditional definition of an organic compound is the compounds or substances that are present in living organisms. And traditionally, it was believed that um, only living things had that vital force to create organic compounds. But then came Wohler. And what Wohler did was he combined ammonium chloride, which is an inorganic compound, with silver cyanide, which is an inorganic compound as well. And he managed to silver cyanide, and he managed to synthesize urea. Now, urea is found in urine, hence the name urea. It's found in urine. And turns out you didn't need that vital force from your body to create it. He took two inorganic compounds and created it anyways. So when he synthesized urea, the definition of an organic compound had to be changed. And now the definition of an organic compound is a carb. An organic compound is a compound in which carbon is attached to hydrogen, nitrogen, oxygen, phosphorus, sulfur, fluorine, chlorine, bromine, or iodine. So organic compounds are when carbons attached to any of these elements. Gonna pause it for now. Now the next question is, what are functional groups, and name a few organic families which contain these functional groups. First thing, a functional group by the name tells you how a chemical compound or how an organic compound will function in a chemical reaction. It decides the chemical reactivity of that organic compounds. Now, there are a number of families, organic families, which have these functional groups, and we'll be talking about these functional groups in detail. A few examples of these functional groups are, now you don't have all of them in your course, but the most important ones. You'll have alkenes. Because you've already discussed this, you would know that the functional group here, what is responsible for a chemical reaction in an alkene? What is the reason for a chemical reaction? Yes, sir, the double bond. So the functional group is the double bond. Then we have already discussed no, we haven't. Alcohols. The functional group here would be the OH group. Then another family is aldehydes. Now this is new to you, but if you paid a bit of attention in last year, we did a little bit of aldehydes. Ketones, esters, yes, so you do remember. I'm glad. Carboxylic acids. Carboxylic acids. Esters. Amines. Amides. We haven't done these ones, but we will by the end of this term. And finally, amino acids. Okay, I'll give you a little bit of time to take this down before I move on to the systematic naming of alcohols. Okay, so moving on now. We're going to start with the first functional group called alcohols. And the functional group in an alcohol is, anyone? Hydroxyl group. The hydroxyl group also written as OH. How do you name it? The suffix that you put for it is OL. Now the numbering position or numbering rule for this one is like any other substituent. Any other substituent, you can use 1, 2, 3. So if the alcohol is at the second position, you'll just say, let's say it's an alcohol which has 3 carbons, and the hydroxyl group is on the second carbon. It'll just be propane 2-ol.
What's the naming rule mean?
This one? Oh, nothing actually. It should come below it. Sorry. So the numbering rule is like any substituent. I have a few examples which I'd like to discuss at the bottom here. So the first alcohol that we are discussing is methanol, which is CH3OH. So what you're just doing is you're replacing the last hydrogen with the OH group. So the alcohol is CH3OH. Now condensed is when you lose the bonds, CH3OH. That's the first one. Ethanol is 2 carbons, 1, 2, 3. I'm not going to put hydrogens here. It'll take too much time, and we just have 15 minutes. Actually, I'll do it. Yeah, I won't do it for propan-1-ol. So CH3, CH2OH. Propan-1-ol, 3 carbons, 1, 2, 3. The OH goes here. Everywhere else you have hydrogens. CH3, CH2, CH2OH. Propan-2-ol. For propan-2-ol, the OH group would go in the center. And yes, and everywhere else you'll have hydrogens. Sorry, I've drawn a condensed structure here just because of the lack of. Okay, no, I shouldn't. I'll just put. Yeah, okay. But then I'm teaching you something wrong. I can't write a structural formula where you have to. Anyways, CH3, CHOH, CH3. For which one? Yeah, it has to be brackets. But then it looks weird, doesn't it? HOH. Is it the HO group or is it the OH group? It's confusing. By putting it in bracket, you make it clear that there are 2 groups attached. One is H and one is HOH. One is OH. You don't say that one is HO, and it's just confusing if you don't put a bracket. Butan-1-ol, 1, 2, 3, 4, OH, and the rest is hydrogen. Okay. If you haven't taken this down already, I'll give you a minute to do that. Now that we've discussed the rules for naming alcohols, now I want to move on to the 3 types of alcohols, which are known as 1-degree alcohols, 2-degree alcohols, and 3-degree alcohols. And the classification is just based on the carbons attached to the carbon bearing the alcohol group. I know that's a mouthful, but I'll just quickly give an example, and that will make it much easier to understand. So a 1-degree alcohol is when you have only, so you have a carbon group here, and then attached to it is the OH group, and this carbon is only attached to one methyl group or an ethyl group, doesn't matter. Just has to, it has a carbon is attached to one carbon, so it's a 1-degree alcohol. Anyone who can tell me the name of this alcohol? Ethanol. Good work, Big T. ethanol. Now, 2-degree alcohols are when the carbons attached to the OH group here, and in addition, 2 carbons. Could anyone name this, please? Propane, 2-all. Perfect. Propane, 2-all or 2-propanol. Both are right. And 3-degree alcohols. 3-degree alcohol is you start with the carbon, attach it to the OH group, then attach it to 3 carbons. This is 3-degree alcohol because it's surrounded by 3 carbons. 3-degree alcohol. Could you name it, please? Methyl, propene, or you could call it 2-methyl propane 2-all. Okay. So if you have taken this down, you should be able to do question 1 and 2 from set 16 Lucarelli. Thanks. Okay, if you've managed to answer the 2 questions, they were like really easy. I mean, really easy. So it's time that we move on to the physical properties of alcohols. So there's a question on the board. The question asks you to explain why the alcohols have higher melting and boiling points compared to their parent alkenes, and you have to explain this with a diagram. Now, a hint to answer this question is go back to what you learned in year 11 in intermolecular forces. That will help you explain why one of these why the parent alkenes don't have as strong a melting or a boiling point compared to alcohols. So I'm going to give you 3 minutes to do a think page share, and then we're going to continue from there. Okay, if you did manage to go back and refer to your year 11 notes, you would have found that the alcohols have what we know as the strongest weakest force, or hydrogen bonding, and that is the reason that you have a higher melting point or a higher boiling point for alcohols compared to the parent alkene. In a parent alkene, for instance, this is methanol. The parent chain here would be methane, or the parent hydrocarbon is methane. Now this will have a relatively low boiling point. It's just because this only has dispersion forces, and this guy has the most extreme case of dipole-dipole force, extreme dipole-dipole, known as hydrogen bonding. Okay, another question that I have written down here is that smaller alcohol molecules are soluble in polar solvents. However, larger alcohol molecules are soluble in non-polar solvents. Now that seems absurd, but how do you explain it using what you know from intermolecular forces? Your time starts now. You have 3 minutes. Thanks. The best way to answer this question would be if you could list down all the forces present in water and a small molecule like methanol. So let's just quickly do that. Methanol has dipole-dipole, DP-DP, hydrogen bonding, and dispersion forces. Water, same thing. All of them are the same. However, when you go up to a bigger alcohol, alcohol molecule, you'd find that the dispersion forces overtake or dominate the hydrogen bonding. And since dispersion forces are dominating the hydrogen bonding, according to like dissolves like, the bigger molecules would be soluble in non-polar solvents which have really high dispersion forces. Non-polar solvents have very high dispersion forces. Now, if you've understood this concept, you should be comfortable attempting question 3, 4, and 5 from set 16. I'll do aldehydes in another video. Thanks.